Okay, so we're going to continue to dive deep into the silicates group for now. So most silicate minerals form when molten rock crystallizes, which can happen at the surface or at great depths, as we will see in the next chapter. It depends. The environment during crystallization, as well as the chemical compositions of the magma from which they crystallize, determine to a large degree which minerals are going to be produced. Some other minerals form at the Earth's surface through the process of weathering, for example, and that we will look at in Chapter 6. And some other minerals form under great pressures that are associated with mountain building events and are typically only formed under metamorphism of the rocks, and that we will cover in Chapter 8. So each mineral has characteristics that suggest under which kind of environment it formed, and hence it provides geologists with clues about the overall history of the rocks of which those minerals are part of. Okay, so now we're going to go over the most silicate minerals, or the most important ones, which are divided into two major groups, or subgroups I should say, based on their chemical compositions. These are going to be the non-ferromagnesians, or light-colored silicates, and the ferromagnesians, or dark-colored silicates. So the light-colored silicates, again called non-ferromagnesians, as the name says, lack iron and magnesium. So ferro is iron, magnesium obviously magnesium, so non-ferromagnesium, lacking iron and magnesium. So they are typically the colors, or I should say iron and magnesium typically give the colors that are darker to most of the minerals. So because the non-ferromagnesium minerals lack these two elements, they tend to be pretty light colored. So hopefully that kind of helps. I might have confused you, but I hope not. So again, non-ferromagnesians tend to be lighter in color as well as lighter in weight. So both iron and magnesium tend to be heavier elements than, for example, calcium, sodium, potassium. So because iron and magnesium tend to be heavier, they also tend to make whatever minerals that contain them heavier. So non-ferromagnesians are lighter in color and in weight because of their lack of iron and magnesium. Okay. So generally, these non-ferromagnesian silicates will have a specific gravity of 2.7 or so, as opposed to the ferromagnesian minerals, which have specific gravities of 3.2 to 3.6, so a fair amount heavier. Okay. In contrast, ferromagnesian silicates are those that do contain iron and magnesium. Because of that, they tend to be dark-colored silicates, and they have minerals such as iron and magnesium, no wonder, which typically bond ionically with the silicon oxygen tetrahedron. So that makes them overall heavier as well as darker in color. Okay, so I know that was a little bit redundant, but it is a pretty good distinction to have now, so that's why I repeated it so much. Okay. So in the next few slides, we'll go through the main minerals for the non-ferromagnesian silicates first, and then we'll go through the ones for the main ferromagnesian silicates. Okay, so as I said, non-ferromagnesian silicates are typically light in color and light in weight. They lack iron and magnesium, and rather the silicon oxygen tetrahedron is bonding with ions such as potassium, calcium, sodium, and aluminum. Okay, so those four. The first subgroup of the non-ferromagnesium silicates that we're going to look at are the feldspar group. So feldspars are by far the most plentiful silicate group in Earth's crust. It comprises about 51% of all of the crust. Their abundance can be partially explained by how fast they can form under a wide range of temperatures and pressures. Two different feldspar structures exist. the potassium feldspars, or K-spars, because potassium is the symbol K, as well as the plagioclase feldspars, or plagioclase feldspars, or simply plagioclase. Potassium makes these end member of feldspars kind of pink, and although rarely, sometimes it also makes it blue-green, which is kind of cool in nature. So these K-spar or potassium feldspars end members are typically called orthoclase or mycocline, depending. And then the plagioclase end members, or plagioclase feldspars, are also subdivided into two smaller end members, one having sodium and one having calcium. I believe that albite is the one that has the sodium, and anorthite is the one that has the calcium, but don't quote me on that just yet. Okay, so despite this difference between potassium feldspars and plagioclase, feldspars overall have pretty similar properties otherwise. They have two-directional cleavage at 90-degree angles. The hardness of both of them is 5.5 to 6 in Mohs scale. The luster varies from glassy to pearly on both of the types of feldspars. And they have a rectangular shape when you see them inside of a rock sample that is typically smooth, like the one you see on the top right over here. So another useful distinction between the two main types of feldspars are striations, which are parallel lines, usually on cleavage planes, which are present on plagioclase crystals, but are not present in potassium feldspars or K-spars. Also, exsolution lamellae, which occurs only on potassium feldspars, not on plagioclase feldspars. So exsolution lamellae, you can't really see the striations on this one, or you can sort of see them, but they're very kind of faded. But you can see the exsolution lamellae lines pretty well on this image here on the left. So they're going to be this kind of white, veiny looking lines inside of that mineral. And exsolution lamellae are these features that occur due to the inner growth of some of the sodium into the mix during crystallization. So although most of that silicon tetrahedron is bonded to potassium, a little bit of sodium does bond to some of the silicon tetrahedrons, oxygen tetrahedrons out there. And so it makes this inner growth in between most of the potassium-rich mixture during crystallization. Another subgroup of non-ferromagnesian minerals are the quartz minerals. So I'm pretty sure that most of you are familiar with quartz, which is cool. So these are the second most abundant mineral in the continental crust, and the only silicate mineral composed entirely of silicon and oxygen. So because of this, usually the term silica is applied to quartz. Okay, in order for the silica, oxygen, or I should say SiO2 to form, a three-dimensional framework is a chemical structure that results. And so it has a very strong lattice, so a very strong structure, which makes this mineral have a hardness of 7 in Mohs scale, which is pretty hard. Very high. This is definitely the highest that you're going to see in lab. So thanks to this property, quartz is very resistant to weathering, for example, and we'll touch on this for sure in chapter 6 and 7. Okay, so very resistant to weathering because of its structure. And when quartz is broken, it typically exhibits conchoidal fracture, but when pure, quartz is clear, and if allowed to grow without interference or any space restrictions, it will develop kind of hexagonal crystals that developed into prism-shaped ends, kind of like you're seeing here, or even in this rose quartz right here. So remember, when it does have different colors that are not clear, it's because of some impurities within the sample. Okay, so despite this cool fact, quartz, like most other clear minerals, is colored by those inclusions of the various ions that are within, which we call impurities. And due to this, it will most often form without developing the crystal faces from the pyramid or prism-like shape. The most common varieties of quartz are going to be milky quartz, which is not in this image, again clear obviously, rose quartz, which is right here, smoky quartz, which is kind of gray to black, amethyst, which is purple, and citrine, which is yellow to brown, and then I guess the clear one we call rock crystal. Another mineral of the non-ferromagnesian silicates is muscovite. You have seen muscovite in a few slides before, so muscovite is of the mica family of minerals, which we will continue to cover throughout the course. So mica is kind of like a subfamily that not necessarily is split into ferromagnesian or non-ferromagnesian, but it has very key properties that have us put both or many of these minerals together. So muscovite is light colored and has a pearly luster. Micas, all of them, have excellent one-directional cleavage, and so it breaks into nice sheets, as you're seeing here in the image. It tends to give sparkle to the rocks that contain this mineral, and this is very apparent in metamorphic rocks, for example, as you'll see them in Chapter 8, and as we'll see them in lab for sure. So due to its nature, muscovite was used in medieval times as window material, but it's not very strong and not very resistant to weathering, so this practice didn't last for very long. Okay, so clay minerals are a set of complex silicate minerals that, like micas, have a sheet structure. So, however, unlike most of the other silicate minerals, clay minerals originate as a byproduct of the weathering or breakdown of previous minerals. So most of the other silicate minerals form from magma that is crystallizing. Clay minerals form as a byproduct of the weathering from other minerals. Okay, but they're still silicate because the silicon oxygen tetrahedron still holds. So due to them being formed in this manner, they make up a very large percentage of the surface material that we call soil, and we'll see this again in Chapter 6. So their presence in soil, and hence overall in agriculture, makes them very important to us humans. Clay minerals are typically very fine-grained, which makes them hard to study unless studied microscopically. So perhaps under a scanning electron microscope or SEM, or through X-ray diffraction. They feel kind of soapy and slippery when you get them wet due to their sheet structure and their weak bonding. They also have are very good at absorbing water in most cases, and so they can expand and contract in the presence or absence of water, which tends to cause a lot of soil problems when constructing on them, because if it is a wet season, the soil tends to expand to a level which you weren't expecting, or the opposite. If it's a dry season, the soil tends to compact too much, and so it causes a lot of construction issues. And so I cover some of these issues in my natural hazards course. I encourage you to take this course if you want to. It's quite good. But again, this quality also makes them a very good resource in many other fields, such as a food industry, for example. So many times they are added to thickened milkshakes, for example, because they retain this water very well and it makes it kind of expand, but still retain that moisture. So clay minerals are pretty great. They have many properties in outer space as well.